guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about manifold learning methods, in which we can will learn some methods for dimensionality reduction. Already we know about PCA that as a method to reduce the dimension of the data. So today we want to talk about another methods for dimensionality reduction. Some of the methods falls into the category of manifold learning, which we will talk about it today. So what does this manifold learning mean? So commonly high dimensional data often lies on or near a much lower dimensional or curved manifolds. What does it mean? We don't want to define manifold mathematically or exact definition of manifold, but to have some intuition about what does this mean or what does manifold mean. Let's say, so this is an unsupervised method, so we don't know the labels, so we showed all of the data with same figures. In here I show them with X. Okay, let's say we have two-dimensional data in this case, but we know that from the figure they are light actually on a one-dimensional manifold. So for example, in this case, this circle is a one-dimensional manifold that these data lied on that. Okay, so now you know probably what does the manifold mean. So this actually could occur in more high-dimensional data, like for images. You could think of, this is one image, this is maybe another image. Only difference maybe is that the hand is something like this and some similar images. So we think that actually these images are lie on a manifold in a space. So as you could see in here, for example, we have two-dimensional space to describe the data in here, but if we find this manifold, then we could describe these data points on the circle with just one number. For example, let's say this is 2 and 1, so we need 2 points, two numbers to represent this data point. But if we find this circle, then we know that we could actually represent this data with just the angle, which is pi over 2 for this data. So from two numbers we could reduce the dimension to just one number. Okay, so if the total data consumes maybe 10 GB on your hard drive, then you could reduce this size to 5 GB and compress that without any loss of your information. So that is so cool. And also this is one reason, and another reason is the occurs of dimensionality. So we know that if we want to pass this data into a classifier, then if from two-dimensional data we could extract somehow one-dimensional representation without loss of information, then the performance, the generalization of our classifier will be better. So this is the reason behind why we want to learn some manifold that data lied on them. Okay, so actually, so manifold learning is a good way to represent data points is by their low dimensional coordinates. So in this example, the 2D space is high dimensional space that the data are laid in that space, but the low dimensional space is one dimensional space in here, that the dimension of the manifold, and we could actually represent the data points on that manifold with just 1D. So we call that low dimensional coordinate. Okay, so the low dimensional representation of the data should capture information about high dimensional pairwise distances. So so let's say after the manifold learning, we will convert these data, this 2D data, and in other words, unravel this circle and convert that to axis and put the points in here. Let's say this is 1, 2, 3, 4. Now we have 1, 2, 3, 4, and so on. So we just unravel and unroll this circle in here to convert that into a low dimensional space. And actually we want to preserve the distances for the neighborhoods in here and in here. Okay, this is actually one definition of manifold, but anyway. Okay, so our general purpose is actually dimension reduction. So we have two general dimension reduction method. The first category is global methods. In the global methods, assume that all pairwise distances are of equal importance. So we don't give weight to neighbors in the data. We just weight all of them the same. Okay, and we choose the low dimensional pairwise distances to fit the high dimensional data. And the second category is local methods. Local methods assume that only the local distances are reliable on high dimensions. So in this case, let's say we have something like this. We will say that in local methods, so the distance between these two are important. The distance between this one and this one probably is not very important to preserve in the low dimensional space. So if we want to convert that into a 1D space, we just want these two to have the same distance, but we don't actually give importance to the distance between this one and this one. This could be here or there, you know. So we call these methods local methods. Okay, for linear methods for dimensionality reductions, we always first study linear models and linear methods because they are more simple to learn, and also as we learned with kernel trick, we could actually somehow convert high dimensional and include nonlinearity with kernel trick to linear models. Okay, so for linear models, we actually learned PCA in previous sessions. In fact, PCA finds the directions that have the most variances. So If we had something like this, then we know that the direction that PCA gives us to as the direction for dimensionality reduction and map the data into this axis is the axis with the most variance components of the data. Okay, so in this direction the data are most scattered in this direction. Okay, and how does that work? So it works by representing where each data point is along this axis. So we minimize the squared reconstruction error to actually obtain this axis. Okay, so this is PCA. The second method that now we want to learn is MDS, or multi-dimensional scaling. Okay, so in multi-dimensional scaling, actually it arranges the low dimensional points so as to minimize the discrepancy between the pairwise distances in the original so we want to actually have minimize the discrepancy between the pairwise distances in the original space and the pairwise distances in the low dimensional space. So as I told before, you want to preserve the distance between data points in here. So you want to preserve this distance, and so on to when you reduce your dimension. So you want to find a mapping in that the distance between 1 and 2 is equal to the the distance between 1 and 2 in this new axis, in this new space. Okay, so you want to preserve the distances in the high dimensional space to be preserved in also the low dimensional space. Okay, an obvious approach is to start with random vectors for y. So let's say the data points in this high dimensional space, we show them with x, and so we want to find the low dimensional representatives, let's call them y's, for the high dimensional data points x that preserve pairwise distances as well as possible. So we want to preserve these distances as well as possible. So if they are x, those are y. So an obvious approach is to start with random vectors for y's. So we start with random vectors in this space, and then we use gradient descent for the cost function to minimize the cost function. So how could we define the cost function? The cost function could be I is less than j dij minus dij hat squared. So I is less than j because we don't want to have because we know that the d12 is equal to the distance between the point 2 and 1, so we don't want to include also this one. So we just calculate I is less than j, and the d hat is the distance in the new space between I and j. So in here, let's say this is let's say this is I and this is j, then this is the ij, and in here when we map the data after mapping, let's say this is I and this is j, and this distance is d hat I and j, and we want to d I and j and d hat I and j is close as much as possible. Okay, so we could say that actually if we want to write it more formal, dij is equal to xi minus xj squared, and dij hat is equal to yi minus yj squared. Okay, so the question is that maybe it is somehow similar to PCA. So is it actually when it is equal to PCA, or what is the relation between this MDS and PCA? If the data points all lie on a hyperplane in a space, then MDS solution is like the PCA. Okay, so if they are on a hyperplane, then the solution of this is like the PCA. Okay, and also if we double center, so let me to write those in here. So first one, data on hyperplane, and the second one is if we double center the data. So double center means that zero mean, row wise and column wise. So if you zero mean row wise and column wise your data, then we call it double center data set. Then in this case also MDS is like PCA, but just note that in this case double centering can introduce a spurious structure for the data set. Okay, so until now MDS is a linear method, but MDS can be nonlinear by putting more importance on the small distances. A popular version is the Salmon mapping actually. So so it means that let me write the cost function for the nonlinear MDS, then we could actually see the difference. So we have xi minus xj minus yi minus yj over xi minus xj squared. So as you could see now in this case, we are putting more importance on the small distances, because when two data points are close, means that xi minus xj is small. So because this is in denominator, then this would be greater, the cost function would be greater, and this means that we want to have we are giving more importance to smaller distances. But the problem of this method is that nonlinear MDS is also slow to optimize, so it is hard to optimize, and so slow to optimize, and also it actually gets stuck in different local optima. So there are lots of local optima that it gets stuck in those local optimas. And Another problem is that it's as you could see, it puts too much emphasis on getting very small distances exactly right. So if we have something like this, then the importance of this in this cost function is so much. So the gradient descent or any other method tries to actually make these 2 points in the low dimensional space close as much as possible. So it could mean that we are losing the importance for other data points. Okay, so we are giving too much importance to the close data points. And another problem is that it produces embeddings that are circular with roughly uniform density of the map points. Okay, so now we want to solve the problem of the local optima for the MDS. For this, we could use isomap. It is local MDS without local optima. So instead of only modeling local distances, we can try to measure the distances along the manifold and then model these intrinsic distances. The main problem is that to find a robust way of measuring distances along the manifold. Okay, so if we can measure manifold distances, the global optimization is easy because we could actually convert that into a global MDS, or actually it's like PCA. So in that case, we could convert the problem into like normal MDS. So what does it mean? It means that we want to, let's say this is point 1, this is 6, this is 4, and in the newest space we have something that we want to have something like this. The distance between 1 and 6, we want to be greater than the distance between 1 and 4. So because we think that on the manifold these are closer together than these are, this one and this one, because maybe in the Euclidean distance between this one and this one probably it is not true, but we want to in this space on this manifold it is true. Okay, so how isomap measure intrinsic distances, this kind of distances? Okay, this is the question. It actually, each data point for each data point in high dimensional space, it connects each data point to the k nearest neighbor in that high dimensional in the high dimensional space, and then put the true Euclidean distances on each of these links. Okay, then the approximation to approximate the manifold distance between any pair of points, it will be the shortest path in the neighborhood graph. So what does it mean? Let's say, so in this case, we first, for each point, we created a graph by choosing k nearest neighbor of each data point. So let's say after creating the neighborhood graph, we have something like this. And let's say this is B and this is A. Okay, so in this case, if you want to measure the distance between A and B, although in the space the distance is this one, but you should actually calculate the distance in here. And for the weights of these links, you use the actual Euclidean distance between these points. Okay, so you just sum this one, and this one, and this one to obtain the distance between A and B on the manifold in isomap. So the maps tries to preserve the information of manifold. Okay, so now we want to have some maps that preserve local geometry, and we want to talk about them more. So the idea is to make the local configuration of points in low dimensional space resemble to the local configuration in high dimensional space that actually we talked about it. So we need a coordinate-free way of representing a local configuration. If we represent a point as a weighted average of nearby points, the weights describe the local points configuration will be something like this. So they are some kind of average of the neighbor data points. And for finding the optimal weights, we could use cost function of this means the neighbors of I wij xj squared, and because this is the weighted average, we know that the sum of all these weights are 1. And here is when LLE comes to play, or local linear embedding. So in LLE, it uses the data path to determine the local weights, then try to construct each latent point from its neighbors. So we only use the high dimensional space once to get the local weights. So in that case, the cost is actually sum over yi minus the weighted average of yj, and in this cost function now wij are fixed weight. Okay, so this is LLE, or local linear embedding method. There are actually lots of other methods for manifold learning, and lots of other mathematical details for these methods, but actually we just want to know the general thing about manifold learning. In the next session, we see some examples in scalearn from MDS and LLE, or local linear embedding, and also we will take a quick look at SNE or TSNE or stochastic neighbor embedding, which scientists and researchers use it a lot to visualize the data, the high dimensional data into 2D space, or for better visualization of the data points. Okay, see you in the next session. Bye.